In general, we can use the difference quotient, which is the slope formula in function format, to represent the slope of the secant line, AROC. So slope of the secant is f of x plus h minus f of x over h. You should have seen that in college algebra. We will actually be doing it in my class in college algebra on Monday morning. And that is the difference quotient. And essentially what it's saying is this. I have two coordinate points. X, the y value is f of x. I'm going to essentially move h units over. So the distance between this x and this x is h units. So I would take x, add h to it. This position is x plus h. He has a y value of f of x plus h. So here's my two coordinate points. I can draw my line. And if you think of how the slope formula works, you draw that right triangle. The distance this direction is h. The distance this direction is, take the long side, subtract this little piece right here, the short side. That gives you the length in the middle. And then I look at the quotient of these two. That's rise over run, and that's this guy. So it's just y2 minus y1 over x2 minus x1, but it's in function format, which makes it more usable for us in calculus. So here we go. If I take a look at this guy, this is algebra. This is essentially the secant line. And what we've been working on is finding the slope of the secant. In the world of calculus, the issue becomes, I want to look at what happens when h goes to 0. That means that this distance begins to decrease and get very, very, very close to the original number. And this close. H goes to 0. This guy's getting very close to 2. 2.1, 2.01, 2.001, 2.0001. You're getting very, 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 very close to 2. Because h is going to 0. So what happens is this. I start out with the secant. And as h goes to 0, I'm moving down along, and I'm pulling secants down along this graph. Because h is going to 0, this line is moving down till we're at a single point. The line that's here that only touches the graph at one point is called the tangent line. Tangent line. So when I'm dealing with the tangent line, I'm only dealing with one point. When I'm dealing with the secant line, I'm dealing with 2 points. Tangent line's 1 point, secant line is 2 points. Now, it's very, very hard to get the slope of a line if you only have 1 point. That means you have to have something that's going to give it to you. Because it does not come naturally. Does not come naturally. So then we're going to define what we're going to be looking for. We call this instantaneous rate of change, IROC, the slope of the tangent line. The slope of the tangent line is the limit as h goes to 0 of this, which is the slope of the secant. Algebra, calculus. Algebra, calculus. Algebra, calculus. Instantaneous rate of change. What it does is it takes a snapshot. Kind of think about Superman going across the landscape. He's flying along. He's speeding, right? He's really booking it, unless they've got some outer space cops up there that's going to pull him over. But he's really booking it. But you've got your camera, and you take a snapshot. That freeze frames him at a point in time. And you can develop what his speed is at that one point in time. Probably a better example is that we're all familiar with is the radar gun. Right. We're kind of booking along, and then we see a cop up in front of him. And he has a radar gun. And what happens? Well, just the fact we see a cop up alongside the road, chances are very good we're going to do what? Brake. Now, my speed has then changed from what it was, right, to where I get ready to go past him. When he takes that radar gun and points it at me, it takes a snapshot of what I'm doing at that point in time. I was going faster before, right, and I might be going slower after. Maybe I didn't brake enough in time, right? But it's just a snapshot of what happens then. Doesn't tell him what I did before, doesn't tell him what I did after. Just what I did when he pointed and he pulled the trigger. That's what instantaneous rate of change is. It's what I'm going at the point he pulls the trigger. What happened before is unimportant. What happened after is unimportant. It's just what I'm going at the time that he clocks my speed. That's instantaneous rate of change. Radar gun's a good example of that. Not that I have had to deal with one lately, but just in case. This becomes the definition of the derivative. This is an apostrophe. F prime of x is what we call it. So we say f prime of x is, it's the slope of the tangent, which is the limit as h goes to 0 of f of x plus h minus f of x all over h. That's the definition of the derivative. That's how you calculate instantaneous rates of change. And this is at any given or specific x value. Because you give me a different x value, rate of change is going to be different. I mean, he pulls the trigger, clocks me. Minute or two later, he pulls the trigger again. And more than likely, I'm not going the same speed. Even if I'm on cruise control, I might not be quite going the same speed. So it's only at that instant, that x value.